Welcome to this explainer. Okay, we're jumping right into some absolutely fascinating digital architecture today. So I want you to picture a highly advanced network, the Internet Computer Protocol, or ICP for short. Now, ICP is incredibly ambitious. It wants its smart contracts, which are called canisters, to step completely out of their own borders. It wants them to securely control assets in outer networks, like the well-established kingdom of Bitcoin or the bustling, highly complex metropolis of Ethereum. But to actually pass through the gates of those other chains, these canisters need to sign their commands with a very traditional cryptographic seal called ECDSA. Sounds simple enough, right? Well, this simple requirement sets the stage for what is literally a brilliant feat in modern cryptography. Okay, let's dive into this, because here is the massive, glaring problem we're confronted with. A standard ECDSA seal requires a single, top-secret private key. It's the ultimate master key. If ICP simply gave this master key to a single node machine to hold, it creates a catastrophic single point of failure. I mean, think about it. If an attacker manages to compromise just that one machine, they can steal the key and completely plunder all the Bitcoin and Ethereum held by the network. It's kind of like leaving the keys to the entire kingdom under a single, obvious doormat. So to solve this, the architects of ICP had to get creative, and they developed an ingenious process known as Threshold ECDSA.
Act 1. The Mountain of the Elliptic Curves.
Right, so before they could even think about dividing this master key, these cryptographic architects had to choose their terrain carefully. And they went with a mystical, looping mathematical landscape defined by this ancient formula. Y squared equals x cubed plus ax plus b. Now, don't worry, you absolutely do not need to be a math professor to understand how this works. Just imagine a giant game of mathematical billiards. You start at a base point on this curve, which we'll just call G. You strike the ball, and it bounces off the edges of this curve a secret number of times. Let's call that secret number K, until it finally lands on a specific final destination point.
Now, what's really interesting about this slide is how it translates that billiards game into actual cryptography. Your private key, that's K. That is the highly guarded, totally secret number of bounces you made. The public key, on the other hand, is Q, the final destination point where your mathematical billiard ball eventually landed. So one is the hidden journey, and the other is just the visible destination. And here is exactly why this specific terrain was chosen. In math, it's called the elliptic curve discrete logarithm problem. Because of the incredibly treacherous, wildly complex geometry of this curve, anyone in the world can see your final destination point Q, but it is mathematically impossible for them to work backward. They literally cannot reverse engineer the trail to figure out exactly how many times you bounced to get there. The journey, K, remains totally 100% hidden.
Which brings us to Act 2, the shattered secret. So instead of letting any single entity hold that secret number of bounces, the private key, the architects decided to completely shatter the secret into fragments using an advanced cryptographic technique called Shamir's secret sharing. They summoned a council of nodes, which we'll imagine as 13 guardians. The master private key was dissolved into 13 distinct mathematical puzzle pieces and distributed among them. No single guardian knows the master key, and no single guardian could even guess it if they tried. However, if a threshold of them, in this specific case, any 9 out of the 13, combining their strength, decide to act, they can perfectly recreate the power of the key.
But here is where the stakes get incredibly high. They added one absolute, unbending rule. The puzzle pieces must never, ever be brought together in the same room. Think about it. If those 9 pieces are ever gathered on a single server to sign a transaction, a clever spy or a hacker could intercept them at that exact moment of assembly. Boom, game over. Therefore, the key had to somehow be used to sign a transaction without ever actually being assembled in one place.
And this brilliantly illustrates our next step, Act 3, the secret kitchen.
I mean, how do you bake a cake without ever putting all the ingredients in the same bowl? To sign a Bitcoin transaction without bringing the key pieces together, the guardians have to do a massive amount of complex, collaborative math. If they waited until a transaction actually arrived to start calculating, the network would just grind to a halt. It would be painfully slow. So, in their spare time, they get proactive. They run what we can call a secret kitchen. Without even knowing what transaction they're going to be signing in the future, they interact asynchronously. They generate random shared secret numbers called nonces, and they multiply them across the elliptic curve. Basically, they're creating these blind mathematical frameworks, doing all the heavy lifting early, safely tucked about in their decentralized kitchen, just waiting for a call to action.
All right, Act 4, the ghost signature.
Okay, let's speed this up. Imagine a canister smart contract suddenly shouts out, "I wish to send 5 BTC to the outer realm." The message hits the Council of Guardians. Because they've already done all the hard work in the secret kitchen, this online signing phase is lightning fast and just flawlessly elegant. Step 1. The request arrives. Step 2. Local alchemy. Each Guardian takes their own hidden fragment of the private key, combines it with the pre-baked ingredient they made in the kitchen, and calculates a signature share. And the most amazing part here? This requires absolutely zero talking between the nodes. Step 3. The public broadcast. The Guardians throw their individual signature shares out into the open. By themselves, these shares reveal absolutely nothing about the secret master key. And finally, Step 4. The fusion. A bystander or the canister itself gathers any 9 of these shares. Through the sheer beauty of elliptic curve mathematics, those shares just perfectly fuse together.
So the crucial point is what happens next. The math is complete. When this fused signature is presented to the Bitcoin network, it looks completely unremarkable. To Bitcoin, it appears as though it was signed by a single person using a standard single private key. It checks the math, everything aligns perfectly, and Bitcoin happily processes the transaction without a second thought.
But we know the truth, right? We know the incredible secret behind that signature. The master private key never actually existed in any single place, on any single machine at any point in time. It was literally a ghost in the machine. It is entirely decentralized, incredibly fast because of the secret kitchen, and fundamentally unbreakable because the secret is never whole. This is exactly how ICP uses advanced elliptic curve cryptography to navigate the multi-chain universe without ever exposing its secrets. Which leaves us with this final, completely mind-bending thought to wrap up our explainer today. If a master key never actually exists anywhere, at any time, can it ever truly be stolen? Think about the massive implications of that for the future of digital security. Thank you so much for joining me to explore this incredible cryptographic ritual, and I definitely encourage you to keep questioning everything you know about how we secure our digital world.